A narrow gauge railway is a railway with a track gauge narrower than the 1,435 mm of standard gauge railways. Most existing narrow gauge railways are between 600 mm and 3 feet 6 in. Since narrow gauge railways are usually built with smaller radius curves, smaller structural gauges, lighter rails, etc., they can be substantially less costly to build, equip, and operate than standard gauge broad gauge railways, particularly in mountainous or difficult terrain. The lower costs of narrow gauge railways mean they are often built to serve industries and communities where the traffic potential would not justify the cost of building a standard or broad gauge line. Narrow gauge railways also have specialized use in mines and other environments where a very small structural gauge makes a very small loading gauge necessary. Narrow gauge railways also have more general applications. Non-industrial narrow gauge mountain railways were common in the Rocky Mountains of the United States and the Pacific Cordillera of Canada, in Mexico, Switzerland, the former Yugoslavia, Greece, India, and Costa Rica. In some countries, narrow gauge is the standard, like the 3 feet 6 in gauge in Japan, Indonesia, Taiwan, New Zealand, South Africa, the Australian states of Queensland and Tasmania, and the 1000 mm gauge in Malaysia and Thailand. Many narrow gauge street tramways are used, particularly in Europe, where 1000 mm gauge tramways are common. History. The earliest recorded railway is shown in the De Re Metallica of 1556, which shows a mine in Bohemia with a railway of about 2 feet gauge. During the 16th century, railways were mainly restricted to hand-pushed narrow gauge lines in mines throughout Europe. During the 17th century, mine railways were extended to provide transportation above ground. These lines were industrial, connecting mines with nearby transportation points, usually canals or other waterways. These railways were usually built to the same narrow gauge as the mine railways from which they developed. The world's first steam locomotive on rails, built in 1802 by Richard Trevithick for the Coalbrookdale Company, ran on a 3-foot plateway. During the 1820s and 1830s, a number of industrial narrow-gauge railways in the United Kingdom used steam locomotives. In 1842, the first narrow-gauge steam locomotive outside the UK was built for the 1100 mm gauge Antwerp-Ghent Railway in Belgium. The first use of steam locomotives on a public, passenger-carrying narrow-gauge railway came in 1865 when the Festiniog Railway introduced its passenger service, after receiving its first locomotives 2 years prior. Historically, many narrow-gauge railways were built as part of specific industrial enterprises and were primarily industrial railways rather than general carriers. Some common uses for these industrial narrow-gauge railways were mining, logging, construction, tunneling, quarrying, and the conveying of agricultural products. Extensive narrow-gauge networks were constructed in many parts of the world for these purposes. For example, mountain logging operations in the 19th century often used narrow-gauge railways to transport logs from mill sites to market. Significant sugarcane railways still operate in Cuba, Fiji, Java, the Philippines, and Queensland. Narrow-gauge railway equipment remains in common use for the construction of tunnels. Extensive narrow-gauge railway systems served the front-line trenches of both sides in World War I. They were a short-lived military application, and after the end of the war, the surplus equipment from these created a small boom boom in narrow-gauge railway building in Europe. Advantages: narrow-gauge railways usually cost less to build because they are usually lighter in construction, using smaller cars and locomotives, as well as smaller bridges, smaller tunnels and tighter curves. Narrow gauge is thus often used in mountainous terrain, where the savings in civil engineering work can be substantial. It is also used in sparsely populated areas where the potential demand is too low for broader gauge railways to be economically viable. This is the case in some of Australia and most of southern Africa, where extremely poor soils have led to population densities too low for standard gauge to be viable. For temporary railways that will be removed after short-term use, such as for construction, the logging industry, the mining industry, or large-scale construction projects, especially in confined spaces, such as the Channel Tunnel, a narrow-gauge railway is substantially cheaper and easier to install and remove. The use of such railways has almost vanished due to the capabilities of modern trucks. In many countries, narrow-gauge railways were built as feeder or branch lines to feed traffic to more important standard gauge lines. Due to the lower construction costs, the choice was often not between a narrow-gauge railway and a standard gauge one, but between a narrow-gauge railway and none at all. Disadvantages: narrow-gauge railways cannot interchange rolling stock such as freight and passenger cars freely with the standard gauge or broad gauge railways, with which they link, and the transfers of passengers and freight require time-consuming manual labor, a substantial capital expenditure. Some bulk commodities, such as coal, ore, and gravel, can be mechanically transshipped, but this still incurs time penalties and the equipment required for the transfer is often complex to maintain. Also, in times of peak demand, it is very difficult to move rolling stock to where it is needed when a break of gauge exists. So enough rolling stock must be available to meet a narrow gauge railway's own peak demand, which might be much more than needed by equivalent standard gauge railways, and the surplus equipment generated no cash flow during periods of low demand. Solutions to these problems of transshipment are bogie exchange between cars, a rolled box system, variable gauge, dual gauge, or even gauge conversion. European standard gauge trains normally use buffers and chain couplers, which do not allow such tight curves, a main reason to have narrow gauge. Therefore, narrow gauge trains normally use other couplers, which makes bogie exchange meaningless. Another problem for narrow gauge railways was that they lacked the physical space to grow. The cheap construction meant they were engineered only for their initial traffic demands, while a standard or broad gauge railway could more easily be upgraded to handle heavier, faster traffic. Many narrow gauge railways were impractical to improve. Speeds and loads hauled could not increase, so traffic density was significantly limited. In the case of Queensland, Australia, the Queensland Rail passenger network has nearly reached its capacity due to the narrow gauge and an ever-increasing population. As such, new lines are to be built, thus negating the original cost savings. Successful railways. The heavy-duty 3 feet 6 in narrow-gauge railways in Australia, South Africa, and New Zealand show that if the track is built to a heavy-duty standard, performance almost as good as a standard gauge line is possible. Some 200 car trains operate on the Sishen-Saldanha Railway in South Africa, and high-speed tilt trains in Queensland. Another example of a heavy-duty narrow-gauge line is the FVM in Brazil. 1000 mm gauge. It has over 100-pound rail and a loading gauge almost as large as US non-excess height lines. It has multiple 4,000 horsepower locomotives and 200-plus car trains. In South Africa and New Zealand, the loading gauge is similar to the restricted British loading gauge, and in New Zealand some British Rail Mark Chapter 2 carriages have been rebuilt with new bogies for use by Transcenic, Transmetro, and Transdev Auckland. Fastest trains. The reduced stability of narrow gauge means its trains cannot run at the same high speeds as on broader gauges. For instance, if a curve with standard gauge rail can allow speed up to 145 km per hour, the same curve with narrow gauge rail can only allow speed up to 130 km per hour. In Japan and Queensland, recent permanent way improvements have allowed trains on 1067mm gauge tracks to run at 160 km per hour and faster. Queensland Rail's Tilt train is currently the fastest train in Australia and the fastest 1067mm gauge train in the world, setting a record at 210 km per hour. The current speed record for 1067mm narrow gauge rail is 245 km per hour, set in South Africa, 1978. A special 2-feet gauge rail car was built for the Otavi Mining and Railway Company with a design speed of 137 km per hour. Curve radius is also important for high speeds. Narrow gauge railways allow sharper curves, which limits the speed at which a vehicle can safely proceed along the track. Costs. Many engineers considered the cost of a railway varies with some power of the gauge, so the narrower gauge the cheaper it might be. This applied also to different narrow gauges, such as the proposed line in Papua using either 610mm or 1067mm. Nomenclature. In general, a narrow gauge railway has a track gauge less than standard gauge. However, due to historical and local circumstances, the definition of a narrow gauge railway can be different. Gauges used. Many narrow gauges are in use or formerly used between 15 in gauge and 1435mm gauge. They fall into several broad categories. Scotch gauge. Scotch gauge was the name given to a 4 feet 6 in track gauge that was adopted by early 19th century railways mainly in the Lanarkshire area of Scotland. Also 4 feet 6.5 in lines were constructed. Both gauges were eventually converted to standard gauge. 4 foot and 1200mm gauges. 4 feet. Glasgow Subway, Paddon Railway, 1200mm. Central Funicular, Gardena Ronda Express, Zagreb Funicular, Rheineck Walsenhausen Mountain Railway, Schlossberg Bahn. 3 foot 6 inch gauge railways. 1067mm between the inside of the rail heads. The name and classification varies throughout the world. It has installations of around 112,000 kilometers. Similar gauges are 1050mm for the Hejaz Railway, constructed in Israel, Jordan, Lebanon, Saudi Arabia and Syria. Only a few lines survive. 1055mm only in Algeria. Meter gauge and Italian meter gauge railways. Meter gauge is the system of narrow gauge railways and tramways with a track gauge of 1000mm. It has installations of around 95,000 kilometers. As a result of Italian law, track gauges in Italy were defined from the centers of each rail, rather than the inside edges of the rails. This gauge was measured 950mm between the edges of the rails and is known as Italian meter gauge. 3 foot 900mm. And Swedish 3-foot gauge railways. 3-foot gauge railways have a track gauge of 3 feet and are generally found throughout North and South America, as well as Ireland and the Isle of Man. 900mm gauge railways are generally found in Europe. Swedish 3-foot gauge railways can only be found in Sweden. 750 mm Bosnian gauge, and 2-foot 6-inch gauge railways. 750 mm and Bosnian gauge railways are predominantly found in Russia and Eastern Europe. The imperial 2 feet 6-inch gauge railways were generally constructed in the former British colonies, such as the Kailani Valley Line in Sri Lanka. These lightweight lines can be built at a substantial cost saving over medium or standard gauge railways, but are generally restricted in their carrying capacity. The majority of these lines were built in mountainous areas. The majority for carrying mineral traffic from mines to ports are standard gauge railways. 2-foot 600 mm and similar gauges 2 feet 1 foot 11 3/4 in 600 mm and 1 foot 11 1/2 in minimum gauge railways. Gauges below 1 foot 11 1/2 in were rare, but did exist. In Britain, Sir Arthur Hayward developed 15-in gauge estate railways, while in France Decoval produced a range of industrial railways running on 500 mm and 400 mm tracks, most commonly in restricted environments such as underground mine railways, parks and farms. Several 18-in gauge railways were built in Britain to serve ammunition depots and other military facilities, particularly during World War I.